Okay, on to question 3. Okay, now we're given another hour output. We're just given this df. We're given all this stuff. Okay. Now this is one of those times where you got to remember how to read this table. So you guys have been working with this table for a while, so you should be pretty familiar with it. But if you're not, go back, read the book, figure out how to interpret this stuff because it's pretty important. And it's made for simplicity. Like they made it look like this because it's easy to read and it gives you relevant information. So let's see, 9, 4, 7. Okay, so we're interested in, okay, for part A, what's the total sample size? Okay, remember df total is n minus 1, right? So n minus 1 equals df total. So we have n minus 1 equals 306. That means that n equals 307. Okay? Easy peasy. Just remembering the definition of degrees of freedom total. How many, part B, how many things does the regression model, because this is a regression reg, SS reg, it's a regression ANOVA. So how many parameters does the model predict? Remember, DFR, DF regression, equals P minus 1. Okay, it's the number of predictors minus 1. Okay, now, same thing. So this is the definition. DF equals P minus 1. So 5 equals P minus 1. So we're predicting 6 things, okay? We're predicting 6 parameters. P is for parameters, P is for predictors, whatever you want to say. Our regression equation is going to be we're predicting alpha, beta 1, beta 2, beta 3, beta 4, beta 5, and that's 6 of them. So beta 5, beta 1 through beta 5, and alpha. Don't forget that. That's the definition. That's all I'm working with. Okay. Now we want r squared. Now again, working from the definition. Sorry, I didn't really need to give this to you, but it's given on the packet. So if I didn't give you this, you could just add these two up to get that same thing. R squared. Now remember, r squared is defined in 2 different ways. It's SSR over SSTO equals 1 minus SSE over SSTO. Same exact thing. Same exact thing. And let's see. The way you can derive this, I'll derive it real quick. It's pretty easy. So SSR, what is SSR? It's SSTO minus SSE over SSTO. Break up this fraction, we get SSTO over SSTO minus SSE over SSTO, 1 minus SSE. So if you only remember one of these, that's fine, because you can derive the other one, but I mean, they both work the same. So, nifty little thing, always helps to know where these things came from. So how do we find r squared? It's this 1060.86 for 3338.4. And that equals 0.3177. Okay. Okay, so what does r squared mean? R squared, what r squared is the percent of variability in y, in y. Remember, your equation is y equals, the true equation is y equals alpha plus beta 1 x1 plus beta p minus 1 x p minus 1 This is the true equation, right? And we're interested in whether or not beta 1, beta p, all those betas are 0, and alpha too, but whatever. We're interested if these are 0. So what r squared is telling us is how much variability in y is reduced by x. It tells us how much variability in y is explained by x. This is, remember, SSTO, this is the total variance, total deviation, S equals SSE, SSR. SSR is the amount of variance that is explained by the regression model. SSR is a good thing. Think of it as good cholesterol, bad cholesterol. Okay, this is a good thing. We want high SSR, because that means the regression model, the least squares regression estimates, B1, B2, A, all that, those are estimates. That means that if R squared is high, that means those coefficients, those predictors are doing a good job explaining the data. We want that. So yeah, R squared is pretty good in this situation, so yes. Okay. Can I erase this? Okay. Remember that. R squared is important. Now we have part D. What's the best estimator of the variance of the error terms? Okay, now remember, MSE is the best predictor of the error term variance. Because remember, the expected value of MSE is sigma squared. Sigma squared is the variance of the error terms. Just remember, this is epsilon, is normally distributed 0 sigma squared, right? Has a mean of 0, variance of sigma squared. So this isn't the true model. So it predicts. I don't know if your teachers have told you this, but that's the truth. This is what it is. And so it's predicting. So if you just remember these two things, and this is in your model assumptions, right? You have to assume that your epsilons, your error terms, are normally distributed with a mean of 0 and a variance of sigma squared. So if you remember this, that's the correct answer. That's just, it's all working from the definitions, all from the definitions. Okay, and the MSE for this is just 7.5918. So that's the best predictor of the error term variance for us right now. Okay, in part E, this is important. These are all pretty important. All of these answers and all these questions will help you on your test, so, or hopefully at least. E. Okay, now remember, what does ANOVA tell us with regression? We want to know the answer to the question beta 1 equals beta 2 equals beta p minus 1 equals 0. At least 1 beta I is not 0. Okay, answering this question. How do we do that? Well, it's a simple MSR over MSE thing, as it is most of the time. So we just have MSR divided by MSE, and oh wait, it already gives us the F statistic. Remember, this is useful. This is how we want it to be represented, because it gives us the useful way of telling us. So F star is 27.947, and F critical, you guys can look that up. It's F of 5 and 300. But I can tell you that, and actually, even Minitab tells you, R tells you. I didn't write this down, but. Okay, what does that mean? That means our p-value is 0.00026. That's much less than 0.05, much less than 0.01. So pretty great. So we do, in fact, reject H0 because with p-value less than 0.05, we reject. So at least one of those not 0. And that makes sense because R squared was so high and our F value is so big. Okay, excellent.
The Teaching Center, UF's Learning Resource Center.